Hello, everyone. Good to see you. I know I'm not Clara, your usual PM, but I'm Angela from the Encode Club, and I am helping cover today while Clara is away. So I would love to invite our two speakers today, Kyle and Bogdan from the DFINITY team. While they are joining the stage, please do drop a little message in the chat. Yeah, say hi. I can see that Clara has put in GM. She'll be leaving later on, hence why I'm taking over today. But yeah, hi Kyle, how's it going?
Hello everyone, it's going good.
Hey. Awesome, good to meet you as well. Hi everyone. Hi Poland. Benjamin says in the chat. Hi from Poland. Hi Bogdan. How's
Hello.
it going?
Not bad.
Awesome. Cool. So if you guys are ready to share your screen and everything.
Bogdan, do you have a set of slides?
Yeah, I have some slides, so I'm trying to figure out exactly how does this interface work, because I'm getting all kind of requests to allow this and all that.
No worries, yeah. It might do that, and you may need to kind of join back in. Oh, perfect. No, it's up. Awesome.
Okay, I think you get to see what I see, I think.
Yes, we can.
All right, so basically I'll do the presentation. So I'll talk about canisters, and Kyle, who's the expert on this, will be able to answer engineering questions, because I'm a researcher rather than an engineer. So my presentation necessarily is going to be a little bit more abstract. So it's going to concentrate on concepts rather than details. And then if there's questions about the nitty-gritty, Kyle will be able to demystify. So, all right. Actually, I'll not be able to see the chat, unfortunately. So I'll look at the chat in between slides, or maybe Kyle can take questions in the chat. All right, so I'm going to talk about canisters, which is the term that we use at DFINITY to refer to what is known in the blockchain space as smart contracts. And before going into the details, just a quick recap of something you probably have seen in the previous talk by Moritz, which is something about the architecture of the internet computer. So the internet computer protocol, if you look at it from a distance, essentially is powered by a set of nodes. These nodes are operated by independent entities, and the protocol itself, what it does, it adds a layer, it adds an overlay, and essentially it groups nodes in subnets in such a way that subnets within themselves run some sort of blockchain protocol, and the ICP protocol allows subnets to communicate securely. So if you zoom in one subnet, what you see is a bunch of nodes all running the same computation and agreeing between themselves on what computation to run using some consensus protocol. So now if you look at what I have described, essentially I've described what you call a replicated state machine. So this is, from a distance, precisely a computer which carries out some computation. Underneath, the computation is replicated on the different nodes that that comprise the subnet. So what I'm going to talk about in this presentation is how can you program this computer. So I'm going to talk about canisters, and my presentation is structured in 3 parts. So first, I'm going to describe what canisters on the internet computer are. How do they look like? Then I will describe how can you go about writing canisters? And finally, and this is, I guess, kind of what the subtitle of this presentation is. So canister smart contracts on steroids. I'll talk about these steroids. So these are what can smart contracts that run on the internet computer do, which differentiates them from more standard smart contracts. So let's move on. So if what I described a little bit before was the concept of replicated computation. So if you look on a subnet, there is a global state that the subnet has. The global state is maintained, is synchronized and maintained, replicated on the different nodes that comprise the subnet. And the subnet computes, so evolves in rounds. So what happens is, at some point, the subnet is in a certain state. The nodes in the subnet agree on what actions should we take next, and then the computation is performed, and the subnet moves to the next state. So think about the subnet state as being comprised of the state of multiple programs, so the state of multiple canisters that are hosted on that subnet. And the block of messages that I have on this slide, which is the agreement on between the nodes on the subnet to execute canisters 5 or smart contracts 5, 9, and 7. And then the subnet applies this function f. This function f tells how should I evolve the state of the subnet, but in particular, this function f has to tell me how should I evolve the state of one individual program. So on the internet computer, we use WebAssembly. So WebAssembly is a virtual machine, so you can think about it as a machine which you can program using some very low-level programming language. So I guess assembly is meant to indicate that. But the idea is that you do not program in WebAssembly. So you should not have to write smart contracts using WebAssembly, but rather you should use some higher level language, for example, Rust or C, and then compile the high level program into a WebAssembly binary file, which is then executed on the WebAssembly virtual machine. So WebAssembly is so this concept was is reasonably recent. I think the paper that described it came out in 2017 or so, and it was designed to support execution of programs in browsers. So this has some two nice side effects. First, because you're supposed to execute programs in browsers and you do not know what the source of the programs is, there's a lot of effort put into making sure that this execution is safe. So, for example, memory safety is ensured by the environment. The execution of programs is sandboxed, and importantly for us, execution of WASM WebAssembly code can be made deterministic. And the reason why it's important for us is because remember that we have all these nodes that need to kind of perform the same computation so that the computation stay in sync. So we can get deterministic WASM computation by turning off some concurrency features of WASM. But other than that, you get the full power of WebAssembly. So this is, you get the safety, but you also get the speed because again, WebAssembly was supposed to allow execution of programs in browsers, and in browsers, milliseconds matter. So a lot of effort was put into making sure that this execution can be done very fast. So on the one hand, you get a slight overhead over native speed. So I think it's about 10%. So there is a slowdown, but it's very small. So this is about execution and starting up programs. So the overhead in bringing up an environment where the program can be run is actually can be done very fast because program validation in particular can be done very fast. And also, I think this is useful for anyone who wants to partake in the ecosystem. WebAssembly is an open standard. So being open, you have a lot of support for it. And in particular, you get a lot of tooling, for example, that comes for free from the ecosystem. So in particular, for example, one would expect to get even more languages on the left side of the compilation arrow than I have on the slide. All right, so so our smart contracts, now I think you can guess our smart contracts are going to be WebAssembly files. And the reason we call them canisters, I think I'm kind of guessing a little bit here why we call them canisters, but the reason we call them canisters is because we pack together the code that powers a smart contract, but we pack it together with the state. So we pack it together with the memory that the code can access, and the memory is kept alive throughout the execution of the smart contract, until the canister, the smart contract is terminated. The code and the state will stay together. So one thing that I want to emphasize at this point is that essentially what I've described is a machine, this WebAssembly machine, which has very powerful capabilities. You get, for example, 4 GB of memory that a canister can use, and it's fast because, as I described, in the context of because it was designed in the context of web. Yeah, so one thing that I should mention about computation. So you get pretty much as much memory as you want. Computation, on the other hand, is a little bit limited. And the reason it needs to be limited is because, remember, computation proceeds in rounds. So once a canister starts executing, at some point it needs to yield. So other canisters, other smart contracts collocated, get to execute. So so you do have a bound, and I think currently the bound is computation that you can get to do 10 billion instructions, which still, both in terms of the computation that you can perform and also in terms of memory you can access, compares well with other blockchains. For example, Ethereum, where these resources are much more scarce and much more expensive. And I'll say something about costs a bit later. So this is kind of the semantic. This is the syntax. So a smart contract is code and memory. I'm going to talk a little bit about the semantics. So what do I describe? So what is the behavior that I describe when I program a smart contract? So in terms of semantics, our canisters behave like actors from the actor concurrency model. And what I mean by that is that these canisters are in a certain state, and computation is triggered by sending them messages. So I have a canister, it gets a message. So what happens at this point? Some changes to the state of the canister happen, and then also the canister decides to send some messages to other canisters. So this is what I said so far is precisely the actor model. So the reason I say it behaves almost like actors is because, like, unlike the actor model where communication is single shot. So when I send a message, I send the message and I'm done. On the internet computer, communication is bidirectional. So when a canister sends a message, it will get expects and it will get a response back. But like actors, canisters are composable. So this model of execution that I described lends itself naturally to building hierarchical microservices. So for example, you can imagine that this canister, the blue and the red canister that I show on this slide, one implements, let's say, a airline booking service, and the other one implements a hotel booking service. And then what I can do is implement a a package booking service where the new service builds on top of the two existing services. So when I get a call to get the package booking, then this translates into calls to booking hotels and booking flights. All right, so Canisters. So our smart contracts are WASM programs. They behave like, so when you write them, you have to write them in this actor model. You have to say, if I get a call, what should the canister do in order to process that call? One thing that I should emphasize is that by itself, WebAssembly does not come with native primitives for accessing files and accessing network and whatnot. Instead, WebAssembly is built with the idea that the host environment where these WASM files are going to be executed, it's the WASM is this environment that will provide these interfaces. So, for example, in the browser environment, there's a component called Scripton, which provides networking access, networking file access on standalone platforms. And I saw in chat WASI being mentioned. There's this WebAssembly system interface, which is an established standard that is being used. On the internet computer, we implemented something called the System API. So you should think about the System API as the component of the internet computer to which the canisters hook in order to get access to the features that the internet computer offers. So here I list some features. So for example, through this interface, canisters get access to more than the 4 GB of heap memory that they can use natively in WebAssembly, but they can now use tens of gigabytes. This is the interface that canisters use to communicate with other canisters. This is the interface that, as you'll see, canisters can use to talk to the world and get cryptographic randomness and whatnot. One thing that I want to point out, and this is important if you do want to write canisters, you could. So the system API level, the system API is also a very low level API. You do not want to. It's not exactly WebAssembly language, but it's still somewhere there. So you don't want to access it directly. You can if you want, but you don't want to do it. So instead, what you do, I guess, if you want to be efficient, is to use CDKs. So the CDKs are essentially abstractions at the same level as the programming language that you would want to use, that abstract away the system API interface. So you don't have to. So for example, if you want to make a call to a canister, there is a function in the CDK which is probably something like call canister and then pass the parameters, as opposed to using the system API where you have to construct the call, deal with all kind of failure modes and so on and so forth. So right now you can use on the IC, you can use CDKs for these 4 languages. So we have CDKs for Motoko and Rust, which are compiled languages, but there is also, I think, there are community provided CDKs for TypeScript and Python. So what I described so far, I described how do you write a canister. So what you do is pick your favorite language which has a CDK for the internet computer. Write your program. You get a WASM module, and which you get to then deploy. So send it to the internet computer. And once there, when invoked, the internet computer will do the linking with the system API. Will compile the results to get machine instructions, and then execute the way I described before. 2 points that I want to mention here. So first, unlike on other blockchains, canisters on the internet computer are upgradable. So we have a notion of controller, which is a party that has life and death rights over a canister, and usually this is the initial developer. If the canister is deployed and you discover a bug, what you want to do, you'd want to fix the bug. If the canister are immutable, then that would be a problem. So on the internet computer, you can actually change the code that the canister is run. And you can do it in such a way that the memory associated with it, so the state that is associated to the program, is kept. Secondly, the canisters need to pay for the resources that they use. And on the, on the internet computer, the currency for paying for these resources is called cycles. And it is important, I guess, to emphasize that the cost of resources is fixed. So there's a table which says the cost in cycles is fixed. So there's a table which says deploying a canister on an internet computer costs, I don't know, 100 million cycles. And the cost of cycles themselves is also fixed in the sense that it is tied to the value of real currencies. You can think about it, 1 trillion cycles equal $1. So if you deploy canisters on the internet computer, then the cost of running it become predictable. And this is in contrast with, for example, Ethereum, where there's all this variation in how much you have to pay in order to execute smart contracts. All right, so we wrote some smart contract, we deployed it, we're paying for it, for running it. Now, how can the world interact with the contract? So the world can interact with the contract using the IC protocol. There's a REST API that you can that you can use to call smart contracts that are deployed, and there's 2 types of calls that you can make. One call is we call them update calls, so update requests, and the idea is that these calls produce some mutation on the state of the smart contract. So necessarily this needs to take some time. Currently, it's 1 second, 2 seconds, and this is needed because the nodes in the subnet where the canister is hosted need to agree on the change. But you can also do query requests. So this is read calls, and these are actually happening at the same speed as accessing the web. And talking about accessing the web, in this picture, what I show is that you can, in order to be able to talk to canisters, you need to be able to speak the IC protocol language. So you need to know the interface, and you need to use it to talk to canister using the specification of that interface. However, there is the architecture of the IC affords more. So in order to access the IC, you don't talk to subnets directly. You talk to something called boundary nodes. So these are kind of nodes sitting around the border of the internet computer, and they play some role in preventing DOS attacks or dealing with DOS attacks, routing calls to, if I call a canister, it's the boundary node which will figure out to which subnet to route that call. And this is the point of this slide. The boundary nodes have the ability to convert HTTP traffic into ICP traffic. So this means that you can actually access canisters using HTTP seamlessly. So a canister you can host a web page on a canister and then fetch it using standard HTTP. Right, and then, so this is one point of this slide. The second point for this slide is that unlike other blockchains, we work with this reverse gas model. So canisters, as I explained earlier, need to pay for the resources that they use. However, users of canisters, so the callers of the canisters, do not need to pay. So in particular, if I deploy a Dapp that is based on internet computer smart contracts, I can get a user base which is larger than the user base of, somewhat sophisticated users that know how to install an extension, and they know that if I click sign, I'm signing something important. So basically, you get the user base for your Dapp now is extended to anyone who has a browser, essentially. Okay, so this is how the outside world can talk to canisters. So now some of the steroids that I was talking about. First is that smart contracts deployed on the IC can actually make outgoing HTTP calls. And this is, at first glance, it seems, okay, so what's the big deal? I think first, to understand why it's a big deal, I think it's interesting to see what the challenges are. And the problem here is that it's this replication that I was describing earlier. So if I have a bunch of copies of a certain smart contract all wanting to make a certain HTTP call, then you have questions like, how many calls should actually go out of the internet computer? Should be one, should be too many, some? And then the converse, when you get answers, if you get answers, what happens if the answers are different? Then how do you decide what's the correct answer? So with this technology, essentially you can implement, you may know about oracles, because you don't need to now rely on third parties. These calls are natively done by the smart contracts that are running on the IC. The second interesting power that you get is you can have your smart contracts control signing keys. So one way to do it, if you don't care about, if you don't look at this slide, one way to do it is I write my WASM program. Somewhere in there, I hardwire a key, and then I use that key to sign, and that's the key that my smart contracts maintain. But that's problematic. So first, it's problematic because generating cryptographic key is complicated. Secondly, managing cryptographic key is complicated. You have to make sure you don't lose it. And thirdly, you have to make sure it doesn't leak. And although our nodes are kind of protected, they are actually, whoever runs them currently can pick into the memory of the subnet, so they can actually figure out if you maintain some keys there. So instead, what you can do is, and this is a feature called threshold ECDSA, chain key ECDSA, so threshold ECDSA. The subnets, there's a subnet on the IC which actually will generate keys for you. So any canister can say, I want to use a signing key. And what happens at that point is that there is a protocol that goes on, and a signing key for that canister is generated, and this key is going to be distributed among the nodes that make up that subnet. And by distributed, I don't mean replicated. I mean shared, right? So the key is kind of taken apart, and each node gets a piece. And then signing does not involve putting the key together back, but there's some cryptographic protocol which, given the shares in a message, produces a signature on the message that corresponds to that key. So now, if you put these two features together, so you can have smart contracts which can make HTTP call outside, so you can connect to arbitrary web services, and so you have smart contracts which can control cryptographic keys. Then you can connect to any site, so any service, any blockchain, for example, that accepts authentication via ECDSA signatures. So there's many other features that we have. There is, for example, the ability to generate distributed randomness, but I thought I have only half an hour, so I kind of kept it to a minimum. So this is the outline of what I covered. So what you should take away from this talk. First, smart canisters. So what are they? They are WASM programs, and they are called canisters because we bundle the code and the state. Their behavior is described by this actor model. So a canister, the way you write it is, you have to describe what should the canister do in terms of memory changes and messages sent when it gets a message from the outside. To write canisters, you can use essentially any language that targets WASM, but to be able to use the system API proficiently, you should use a language which has CDK support, and we currently have CDK support for Motoko, Rust, Python, and TypeScript. In terms of what canisters can do, so these are features that I think differentiate the smart contracts on the IC from smart contracts on other blockchains. So canisters can actually serve web pages, so you can talk to canisters using HTTP. Canisters themselves can make calls, HTTP calls to the outside world, so they can connect and learn about the Web 2.0 sites. They can control cryptographic keys, and the resources that that they consume are paid with the cycles. But importantly, the cost of running canisters is predictable. So kind of a consequence of what I just described is that on the internet computer, you can deploy dApps, which are entirely hosted on the blockchain. It's both the backend and the front end, because you can serve the front end from a canister. And this is in contrast with, I guess, I don't know if it's common practice, but it's quite a used pattern, where the backend is hosted on a chain, on a blockchain, but the front end is hosted on some cloud provider. And then there's a question of how do you make sure that that front end is not tampered with, and what the front end shows you is what it is supposed to be showing you. So here's 3 applications that for which I had QR codes, so you can try to play with them. So they're definitely, OpenChat is fully hosted on the IC. Discover, I think it's hosted on the IC, but now, it is hosted on the IC, but now it is also talking to the Solana blockchain. And Cryptopia, I think it's some sort of Minecraft-like game. So this is what I wanted to cover. I saw there's a lot of activity in chat, but I didn't have time to check, but I assume Kyle was on top of it. So
yeah, we've got some things to go over. Some of it is a little more directly related. So I'll read you off a couple questions that I think you can answer well, and then we can jump into some of the more developer-y questions. So Alina asks, what is the process of block building? They were looking for an article about that and saw a diagram that describes the canister's role in it. But can you describe just an overview of how the ICP builds new blocks?
So block building happens at the lower level. So block building is essentially a consensus protocol, or so I can describe okay. So let me tell you kind of the steps. So at every round, the nodes involved in the subnet get a random tape. So this is kind of a source of randomness. That source of randomness selects one of the nodes in the round as being the block maker. The block maker constructs the block and then broadcasts it around, and it needs to get enough signatures from the members of the subnet in order for the block to be approved. And then that's it. So, but all of this happens below canisters. Canisters don't see. All they see is that a canister. I got a message and I have to execute it. So there's our white paper describes our consensus protocol. So this protocol where the nodes agree on what should be the actions that the subnet would take next.
Yeah, so I think the high level answer is canisters themselves don't necessarily have a concept of blocks. That's something that the internet computer abstracts away for you. Unless your canister specifically implements something like a ledger and then has its own logic about blocks that it needs to keep track of. And then, yeah, the ICP white paper is a fantastic resource, totally worth a read if you're into this, the nitty-gritty of this stuff. Let's see. I think then some of the other questions, there's a lot of fun stuff to talk about here, but I don't think it's as directly related. There's one question in the chat. Zohaib asks, is there a variance in cycle consumption when invoking system APIs directly compared to utilizing any CDK. I think that might be like something as if like if you were able to do like an ECDSA signature via like a system call versus a library that you had.
So I was kind of hiding some stuff. So
Yeah.
the signatures themselves are actually not in you. You have to use the system API to make a call to another canister, and that's where the expensive stuff happens. So at least for signing, you will not notice a difference. And here I'm going to guess. I think Kyle is gonna confirm or infirm what I'm saying. Is that you get a little bit of overhead if you use the CDK, but the overhead should not be significant.
Yeah, and I mean the overhead should be pretty minimal in terms of like what you need to include there. But honestly, like if you're able to do something without using the system calls, which have specific prices associated to them, the pure computational cost will probably be lower. But at the same time, there are definitely some security reasons why it's better to use the system calls, like, you know, not having access to truly private storage because of the decentralized nature of node providers. So with that, I think now's a good time to jump into just kind of the general Q&A. We can go by ranking of questions. So everyone please jump in and upvote the questions that you think are the most interesting. The first one we've got, which was asked by Arnav, has 5 upvotes, and they ask, what language is best to build on ICP, Rust or Motoko, and what's the difference? Best is obviously a loaded question. Languages have different purposes and preferences. I personally do a lot of Motoko development, and we have people at the DFINITY Foundation and in all of these groups that we work with who have their own choices that they make depending on what they're building. I think I'll break down the what to choose for when as if you're writing a relatively simple application from basically no assumptions, you can just write all application logic. Motoko is actually a very nice language to work with. It maps very closely to just the actor model of the internet computer, and it was designed for internet computer applications. It also feels fairly friendly to someone who, like me, who has a lot of JavaScript experience or just pretty much any C family language. But once you start to get into fairly complex, very data-heavy applications where the structures of your memory become a lot more important, Rust tends to become a better choice for a lot of those applications. And particularly if you have libraries in the Rust ecosystem that you want to use, that's another strong competitive edge because the Motoko library and package ecosystem is still pretty young. So that's kind of how I would choose which one I want to pick, but otherwise it's based on preference. I think there's obviously a great case that like Rust is a really exciting language. It's nice to have on your resume if you're considering general career development. So that's something to keep in mind as well. Let's see. We've got a question from Giovanni. Are there standards in place like ERC20, ERC721, and so on? Yes, we've got a couple. We've had a couple takes on how to do this. From early days, we had a group in the ecosystem who were the Psychedelic DAO. They proposed some DIP standards. So we had like a DIP20, DIP721. That has not necessarily caught on. So there is an EXT standard for NFTs that's still pretty popular since early days. But now we have a set of standards, which are the ICRC systems. There's probably a link that we could provide to just a list of those. But yeah, there's ongoing discussions. We've got things for ledgers. We've got things for proposals for lots of different types of structures that need to be agreed upon. And because we're not really doing specifically Ethereum stuff, it's not going to literally be ERC20, but there will be an internet computer equivalent for a lot of these.
Well, for the equivalent of ERC20 is ICRC2. It just happened that it was the second standard we discussed.
Yeah. We had a few people ask, like, if code is mutable, like, what are the risks involved with that? The fact that a canister can be upgraded. That's a great call out. This is something that is different from a lot of traditional blockchains and smart contract systems. And we have some strategies that are in place for how to deal with this. So the first thing is, as long as a canister just has an arbitrary controller, yes, it is upgradable. Yes, that does create risk to the users, right? Someone could deploy new code that changes the behavior and the assumptions of how the contract works. So that's something to be aware of as a user. A lot of these platforms like OpenChat, or not OpenChat, but like Discover and Cubetopia, because those are still privately run, they're basically just like any other website where someone could deploy something new and change how it works. So if you are holding assets inside of those and you're not actively linking them with like an external wallet, yeah, there's things that you could be concerned about there. However, we do have some strategies for getting around this. So what we do is basically one of two things. You can either remove control of the smart contract entirely, making it unupgradable. You can do this at any point by just simply removing yourself as a controller. Any controller can do this. But there's also sometimes having an upgradable contract is desirable, right? Something like OpenChat, a chat app, you want to continue development indefinitely. So you need a process for how do we get these upgrades out. And the general solution has been to use a DAO. Really any kind of like multi-sig solution or whatever kind of decentralized trust authority you want to use is viable. There's some really cool experiments out there in the community for ways to do this. But one great option that OpenChat has gone through is to launch as an SNS on the through the NNS system. That is kind of like a system level special DAO. It comes basically pre-configured with like tokens and voting rules and proposals all sort of set up for you. And you can use that to upgrade the canister code. And yeah, take away that risk factor of just malicious code getting pushed. At least reducing it, right? It has to be voted on to be adopted. Let's see here. So there were a few questions about that. I see another question from Karthi. Can a canister act as a database? Meaning, do you have a built-in canister today that can act as a relational database, like Maria database or SQL server? Yes, we've got a couple options out there. We have, someone has run SQLite inside of a canister and made that available because that could be compiled to WASM. But the more generic approach has been to use one of a couple IC native platforms for data storage. I can recommend CanScale or Juno as a couple good options to look into. These options have like arbitrary data structures that can be defined and upgraded, and they also have logic for automatically scaling into a fleet of canisters that you can then manage all of the cycles and keep track of. Because at a certain point, we do keep pushing the storage limits of what a single canister can hold. But at a certain point, you do scale beyond the bounds of what a single canister will operate on. And so, yeah, those will serve for you as a way that you can just store arbitrary scaling amounts of data. Let's see. Giovanni asks, what are the requirements to run a node? Basically, there's on the internetcomputer.org website, there's a list of just the flat out hardware requirements. There's a whole process where as long as you get your hardware together, and then you make a proposal sort of explaining, here's my business, here's where we are located, because the Internet Computer doesn't want to co-locate in the same location too many nodes. That way that our system can not only be distributed by who owns the nodes, but also where they're located in the world. That's important for both performance and security reasons. But basically, you put a proposal to the NNS DAO, the central governance of the Internet Computer, and then if you get voted on, you can be added into a new subnet as the next time that one's created. Richard asks, is the code in Canisters public and available to check? Not always. There's no requirement for the code to be public. A hash of the WASM will always be available. That can be inspected at any time. And so that way you can also see if the history of the canister has changed. But a canister can choose to be private. But for the sake of like trust, it is often a very good idea if you are building to share your canisters code, at least for anything that's critical, like a store of data, where trust is of a high importance. So you've got a scale of, I just deployed a thing and don't worry about it. It is what it is. You can use it or not. Great for like a first project or something that you're doing. But the levels of trust scale up to the point where the highest level that we recommend is publish your code base, create a reproducible build system using something like Docker to produce the actual WASM module in a way that someone on their own computer could reproduce. And then what they can do is they can run that build system and verify themselves that the WASM module that they produce from that source code matches what is running in the Internet Computer. And that's kind of like the highest level of trust that you can have, that a verifiable contract is running on the Internet Computer. Yeah, I think it would be interesting to have like an external audit system that does this kind of verification that you could check against. But, we're still early days for that kind of level of tooling. Karthi asks now, if we host a website on a canister, do the users of the website have to have an ICP identity to log into the website? I understand that users can just browse a website. I'm speaking of a case where a login by a user has to be performed. So no, they don't need to have an ICP specific identity. Really, when we talk about an Internet Computer identity, all that we're talking about is having some kind of cryptographic identity on like one of the few curves like ECDSA or ED25519, or specifically SecP256K1. But you have an identity that is able to produce signatures, and then that being able to then make authenticated calls to the Internet Computer. Once you've got a secret that you can reproduce reliably, you have a way to have that secret identity. So a seed phrase can do that. A traditional login flow with a username and password can give you kind of a traditional auth token that you can then use to make authenticated calls. There are a number of strategies with differing levels of risk that you can evaluate for the good of your users. But also traditional wallets such as MetaMask and other sort of browser extension, whatever approach you want to take. There's a lot of people competing for like the best user experience in that space now. really anything that you can use to create a signing identity can be plugged in to make calls to the internet computer. We're very not picky about that. But internet identity is one way that the internet, that DFINITY has provided, which gives you a unique principal on every single website, which has a lot of nice trust properties. Really, the main disadvantage is that if someone is brand new to the IC ecosystem and they haven't set one up before, the setup process can be a little more painful compared to like one-click login with Google expectations that users may have. So yeah, explore a bunch of different options. There are a lot of valid ways to authenticate your users. Is there anything like Etherscan to check transactions and smart contract deployments, and also to publish smart contract code? Yeah, we've got, I'd say, two different, that was Giovanni's question. You can go to dashboard.internetcomputer.org. That's a great place to go look up like canisters and canister history, as well as the contents of their contract. There's also a couple others that are in various states of functionality. They've like gone down before, but I'll definitely recommend dashboard.internetcomputer. And then to publish your smart contract code, we have a couple things. You can work with something like Juno, juno.dev, I believe. Maybe it was juno.build. Juno.build, yeah. That'll give you a dashboard where you can deploy some basic applications using a browser. You can create canisters using the NNS Dapp, and I think we're exploring publishing some pre-built WASM out of that as well. But then there's also the Motoko Playground, which is a fantastic tool for writing Motoko code that you can deploy contracts for free from. Because we reserve like a pool of canisters, and we can just push your code up to them and let it run for 20 minutes before recycling it. So that's another great way that you can kind of get started without downloading anything. Youssef asks, what about the DNS if I create a website using IC? By default, your website will be available at the canisters id.ic0.app. That'll just be available to you for free. But because anyone can kind of publish whatever they want to that URL, we do our best to deal with like takedown requests, but it can still be flagged as like a malicious URL. So it's a great idea to use your own, and there is documentation about how to use your own custom URL with the internet computer. That involves writing a custom service worker, doing a build of that, which I have great news. We're going to be getting rid of the service worker soon, so that process is about to become simpler. But that's the current process today. So definitely refer to the docs, and hopefully in like the next couple of months, that'll simplify considerably as well. Timmy asks, there were a few questions about contract mutability. Didn't quite catch your answer. Yes, so to repeat for clarity, contracts are mutable by default. If there is a controller that was the original creator of it, then it is still mutable, and you should consider it suspicious. But you can do a couple things. You can remove the controller. There is a thing called a black hole canister, which just really exists to report the status and cycles balance of other things, which has like a slightly elevated level of permissions, but you can black hole a canister so that you can at least keep access to those things while still leaving it immutable forever. Or you can use a DAO to gate the upgrade process for your canisters. And if a DAO is in control of that, then you have to at least put it to a vote before you can do upgrades. So those are kind of the 2.5 solutions that are out there for that.
There's a question by Piotr. As we know, the cost of all activities that the container is expected to execute, do we supply it with an exact number of cycles needed? What happens with a used container?
Yeah, so there's a process for rundown. So let's say that I've reserved like 50 gigabytes worth of data, and so my canister is burning through cycles pretty fast. The process of what's going to happen is the canister will continue executing up until a freezing threshold is met, and that does scale according to like the estimated usage based on things like the storage that you have allocated. Once the freezing threshold is met, updates will stop processing on the canister, and it will continue to burn through that threshold until the point where it reaches a cycles balance of 0, at which point the canister will be uninstalled, but it will, so the WASM module will be uninstalled, but the address is reserved indefinitely. The controller of that address is still allowed to install a new WASM module and get things running again in the future, as long as they top off the cycles balance and get it going again. I think the system provides for up to 10 years, at least 10 years that it'll be reserved for. But at the current state of things, it has, it's effectively an indefinite. We will always, no one's ever going to be able to install another canister at the same address.
And then the first part of the question is, do we supply it with an exact number of cycles because we know how much the canister spends?
Yeah, there are ways that you can do that. There's various types of tooling. I think there's the go-to standard right now has been just to kind of top off a specific balance and let it run down from there. But there are ways in which any call that a canister makes to another canister can include cycles with that. And so you can have systems where instead of like the developer provides a balance and runs it down, but instead you charge for every call the specific amount that you know it will cost. And that way that you're fueled just by the cost of every other contract paying its own way for your computation costs. I haven't seen too many of those built, but it's a viable pattern that I think is interesting. A couple, we're done at 10:30, right? So I'll try and like rattle off the next few questions really quick.
Perfect.
Is there a way to allow authenticated users to access certified assets uploaded via ICX asset tool? Not exactly. We've talked about this, but with the default tooling, we don't do that yet. It takes some not super difficult upgrades to make that happen. But I think that that's a very cool path to go down. I'd be happy to talk to you more in the Discord. Karen asks, is CKBTC available on testnet if I want to integrate? Yes, you can check our docs. We have testnet CKBTC available for development purposes. David Lopez asks, for the front end, how free is the front end to work with and can libraries be implemented? Considering the front end will be on chain, storage costs, yada, yada. Yeah, you can totally use design systems and a lot of front-end frameworks. I have examples on my GitHub for how to work with React, Svelte, Vue, Vanilla.js, and I didn't do Angular because I don't like it. But the costs can be very small. For example, I've deployed a very simple asset canister, a front-end that has like an auth client demo integrating with Internet Identity. I deployed that 2.5 years ago, and it has cost me about 30 cents to date in total computation costs. So if it's a small website, it can be very cheap. It'll be things like larger assets like media, images, video, that'll really start to like change the costs. But for simple delivery of assets, it can be very cheap for a long time. And I think that is everything.
Yes, I think that's all the time we have at the moment. I'm so sorry, everyone. I know you guys have so many questions, which is so awesome to see. But of course, come along to the next session. I'm sure you guys will have lots of questions then as well, and stay in touch on Discord. Thank you so much, Kyle and Bogdan, for the awesome presentation. That was really cool, and just your engagement overall. Really fantastic to see. Matthias in the chat also feels the same way. Awesome. Yes. Really great energy, guys, and hopefully see you in the next one. Cool. Thank you so much.
Bye-bye.
Bye.